Assalamu alaikum. Bismillahirrahmanirrahim. Another class of chemistry, first year, that is 11th class. And today we are going to talk about liquid physical state of matter. You are watching before you on screen reduced syllabus. Only these topics have been included in your 2021 examination. Intermolecular attractive forces, dipole-dipole interaction, London dispersion forces, hydrogen bonding, and liquid crystals. Everything about liquid crystal, which is part of your 2020 edition book of chemistry. So first of all, introduction. Simple definition of liquid is given. It is a material that assumes the shape of container without filling it completely. In here, definition of gas and solid state has also been given. A gas, on the other hand, takes the shape of the vessel. I try to highlight it with different color, yellow color. A gas, on the other hand, takes the shape of the vessel and has the characteristics to fill it completely. And next comes solid. A solid neither takes the shape of the vessel nor fills the container completely. So I try to highlight it with some different color. For example, with this pink color, solid neither takes the shape of the vessel or fills it completely. Neither fills container completely. So solid had definite shape and definite volume, as well. Liquid has no definite shape but definite volume, and gases have no definite shapes and no definite volume. That is another way. Another thing, that among these, intermolecular attractive forces in the solid state are maximum, and strongest attractive forces are present among the particles in the solid state, and weakest, of course, would be in gaseous form. So we move on to next slide. What are intermolecular attractive forces? Forces of attraction among the molecules of a liquid are called intermolecular forces. You can generalize this definition by writing in this way, that forces of attractions among the molecules of a sample of matter are called intermolecular attractive forces. Water exists as liquid due to intermolecular attraction, which is a type hydrogen bonding. So in your syllabus, only three intermolecular attractive forces have been included, and which are part of your syllabus: dipole-dipole attractive forces, London dispersion forces, and hydrogen bonding. So we shall discuss these three forces one by one in our next slides. So we move on to next. First type of intermolecular attractive force is dipole-dipole forces. Polar molecules have charges at different parts of molecule. Due to these charges, they attract each other. So how can you define attractive forces? I try to highlight it. The attractive forces between the positive ends of one molecule and with the negative end of another molecule is called dipole-dipole forces. Dipole arises in a molecule due to electronegativity difference. For example, HCl. In case of HCl, chlorine is more electronegative than hydrogen. Electronegativity of chlorine is 3, whereas electronegativity of hydrogen is 2.1. So chlorine is sufficiently more electronegative than hydrogen, as a result of which chlorine will attract shared electron pair that is shared with hydrogen. Mutual sharing is taking place, and as a result, covalent bond is formed in HCl, and chlorine attracts that shared electron pair more than hydrogen, as a result of which chlorine acquires partial negative charge and becomes negative pole, and hydrogen acquires partial positive charge and becomes positive pole. Because there are two positive negative charges poles, so that's why the name is dipole. This dipole, positive end of this dipole attracts the negative end of other dipole, and as a result of which dipole attractive forces are generated. Strong these dipole forces, greater would be value of thermodynamic property parameters like melting point, boiling point, etc. We move on to next. This is the type of force, London dispersion force, which is present among the all molecules, but it is present and it is the only force that is present in non-polar substances, and since other forces are absent, so this force is prominent there. So it is named after the name of scientist London. The force, this is the definition of London dispersion forces here. I highlight it. Forces of attraction between an instantaneous dipole and induced dipoles are known as London dispersion forces. So, I can explain in coming slides. Force of attraction between non-polar molecules which become polar for an instant are called London dispersion forces. We are familiar with monatomic gases like helium, neon, argon, krypton, xenon, and some diatomic gases like halogens, fluorine, chlorine, bromine, even hydrogen H2 and oxygen. These are all non-polar substances, and since they are non-polar, so there would be absence of any other force like dipole hydrogen bonding, and London forces are the only forces which are present here, and proof of their presence is that these gases can be liquefied, can be solidified, so it means that there are some sort of attractive forces are there, and the force of attraction that is in case of non-polar substances, these are instantaneous dipole, induced dipole, or London dispersion forces. We move on to our next slide. Here it has been explained. I pick up green color because green color is not present in this slide here. This one is the right side. I highlighted this one. This one is unpolarized molecule. Electron cloud is symmetrically distributed around the nucleus. Every side has equal charge at a particular instant. Sorry, electron cloud becomes at one side more than at other. For example, in here, electron cloud is more located in this side than in this one. As a result, we can say that here instantaneous dipole is created. When this instantaneous dipole is created, the positive end, which is having a surrounding, you may say that less number of electrons on the right hand side, it will attract the nearby electrons of nearby atoms, and as a result polarity is induced in the neighboring atom or molecule, so non-polar molecule, which is, so that is I try to further explain it, that is here instantaneous dipole, and next due to which a dipole polarity is introduced or induced in the next molecule, that is induced dipole. So induced dipole, instantaneous dipole, force of attraction among these is called London dispersion force. Similarly, this molecule or this atom may induct polarity in the neighboring molecule, that is here this one is introducing induced, this one is induced, this one is induced, this one is instantaneous. It is further explained in our next slide. Here you can watch that electron cloud this in A is concentrated on one side. This one side I am shown with green color. Here charge density is high as compared to right side. Since electrons are not symmetrically distributed around nucleus, so left hand side will acquire partial negative charge because electron cloud is here more than on the right hand side, and right hand side acquire partial positive charge. So this is instantaneous dipole, as a result of which molecule or atom B passing by molecule or atom A, which is instantaneously polarized, it B is also got polarized, and you can see in the product that due to this positive end, this positive end is elected electron from nearby atom, and dipole has been created here. So electrons are at this side in case of B here, and it become partial negative and partial positive. So the B is what is called induced dipole, and A is instantaneous dipole. So such type of forces are called London dispersion forces, or instantaneous dipole, induced dipole forces. What are the factors which affect the London dispersion forces? Three factors have been given in your textbook: atomic or molecular size, polarizability, and number of atoms or molecules in a number of atoms in a molecule. So first factor, atomic or molecule size. Strength of these forces depends on the size of electronic cloud of the atom or the molecule. With the increase in size of atom or molecule, dispersion becomes easy and these forces become prominent. For example, inert gases, helium, neon, argon, krypton, xenon, as we descend, as we move from top to bottom in a group, there is induction of another shell, and size of these gases is continuously increasing. When the size of the atoms increases, it becomes easy for them to distort or to become polar. So as we move down the group, number of electrons are increasing. That's why strength of London dispersion forces is increasing. That's why their boiling points are also increasing. Helium has minus 268, neon has minus 245, argon 1, and so on. So with the increase in atomic size or molecule size, electron cloud becomes distort more easily, and more electrons are on one side than at the other. As a result, we have stronger London dispersion forces, and due to which the thermodynamic parameters like boiling point, melting point, these values increase as well. We move on to second factor, that is polarizability. Polarizability of an atom or molecule is a measure of the ease with which electron cloud or electron charge density can be distorted. Larger atoms have more electrons and larger electron cloud than small atoms. In large atoms, the outer electrons are more loosely bound. As the number of shells is increasing, distance of outermost electron from the nucleus is increasing. Hold of nucleus that is positively charged becoming weaker and weaker. As a result, distortion becomes easier. So this measure of the distortion of electron cloud is called polarizability. It increases with increase in the atomic or molecular size. So example for this is given halogens. You know that fluorine, chlorine, bromine, iodine are halogens. Both all these are diatomic molecules, and all these are non-polar. Fluorine, small size, only 2 shells in there, so it has weaker London dispersion force. That's why it is gas at room temperature. Same is the case with chlorine. However, in case of bromine, you find that bromine is liquid at room temperature because it has more number of electrons. Its polarizability is more than that of chlorine, fluorine, as a result of which it has stronger London dispersion forces, and due to which it exists at room temperature in liquid form. Whereas iodine is solid. Iodine, bigger atom is iodine, more electrons are there, more polarizability is there, stronger London forces are, so it exists at solid at room temperature. Since halogens are non-polar, so their only their physical states, gas and liquid state, only can be explained in terms of London dispersion forces. What a beautiful example is this of halogens constitute for polarizability. Next, we move on to number of atoms in a molecule. Hydrocarbons are non-polar. Carbon electronegativity value 2.5, hydrogen 2.1, and they are generally considered as non-polar. So if they are non-polar, it means there is only London dispersion force among these molecules. So we can judge that as the number of atoms are increasing, their physical state is changing. First four alkanes more accurately, methane, ethane, propane and butane are gases at room temperature, whereas from pentane to heptadecane, C17, C18 up to those hydrocarbons, they are liquid, and later on they become waxy solids. These physical states indicate that with the increase in the number of atoms, strength of London forces is increasing, and due to which physical state is changing from gases to liquid to solid. I think that you at least have two hydrocarbon as an example in your mind. One may be ethane with boiling point minus 88.6, and other hexane which is liquid, and its boiling point can be noted here. So you should keep in mind these two, and you should reproduce them while in your examination if something about factors affecting the strength of London forces has been asked. Next comes our second and very important topic, that is about hydrogen bonding. The crucial thing is that there is hydrogen. Hydrogen is one of the smallest. Hydrogen is the smallest atom of the periodic table, and it can approach to the other atom very closely, and due to which if it forms a sigma bond, that would be a very very strong sigma bond because of small size of atom. In fact, it has only one s electron and only one proton, so one shell is there, and that is to take part, this electron is to take part in the process of bond formation. So due to this, it can approach to other molecules as well because of its small size. That is something crucial. Hydrogen bond is attraction, that here I try to highlight it. Sorry. A hydrogen bond is the attraction between the lone pair of an electronegative atom and hydrogen atom that is bonded to either nitrogen, oxygen or fluorine. These are very electronegative elements. When hydrogen is covalently bonded to fluorine, oxygen or nitrogen, electronegativity of fluorine is, you know, that 4.4, that is the highest, oxygen 3.5, nitrogen 3. These elements are very electronegative elements. When hydrogen is bonded to these elements, it becomes sufficiently positively charged. Now hydrogen bonded to these elements covalently, having sufficiently positive charge, can approach to the lone pair of another atom which may be present in the same molecule or which may be present in some other molecule, and can interact with the lone pair of that other atom. So it's this attraction between the lone pair of an atom, electronegative atom, and partially positively charged hydrogen atom that is bonded to electronegative atom is called hydrogen bonding. Hydrogen bonding is the strongest intermolecular attractive force. Dipole-dipole forces are weaker than hydrogen bonding, and London forces are generally even weaker than dipole-dipole forces. Exceptions are always there. Hydrogen bonds are not covalent bonds. They are sufficiently strong interactions, but they are weaker than covalent bonds. So we move on to our next. Here beautifully explained hydrogen bonding. You can find here purple color. That here is with purple color, with blue color I have highlighted in purple color dashes you are watching, and hydrogen bonds, words hydrogen and bonds are written in the purple color. So lone pair is on electronegative oxygen atom. On the other end, this hydrogen is bonded with electronegative oxygen atom. Due to its bond with oxygen that is very much electronegative, second most electronegative element of the periodic table is oxygen. This hydrogen acquires partial positive charge. I explained this. This hydrogen acquires partial positive charge, and you know that this oxygen of course is partially negatively charged. Now this partially positively charged oxygen forms hydrogen bonds with this oxygen. Partially positively charged hydrogen that is bonded with electronegative oxygen interact with the lone pair of other electronegative atom of other molecule. There may be intermolecular hydrogen bonding. Intermolecular hydrogen bonding is also there, but in this particular case we are talking about intermolecular hydrogen bonding in case of water molecule. Same hydrogen bonding you observe here. Here this hydrogen is and this oxygen is. Same hydrogen bonding you are observing here. Same hydrogen bonding you are observing here. So in all these cases, you know that central water molecule, there are two hydrogen which are partially positively charged. They are forming hydrogen bonds with lone pairs of oxygen, and at the same time there are two lone pairs on oxygen atoms which provide sites for hydrogen bonds to other hydrogen atoms of other molecules. So due to two hydrogens of central water molecule, two hydrogen bonds, and two lone pairs provide sites for two hydrogen bonding. So this is a beautiful explanation of hydrogen bonding in case of water molecule. If you put ammonia in water, then of course similarly as for example this hydrogen is, so in case of ammonia, in case of at the place of oxygen there would be nitrogen, and hydrogen will form in this hydrogen bond in the same manner, and here in case instead of oxygen there would be in ammonia there would be one lone pair and nitrogen there. So we move on to our next slide. Applications of hydrogen bonding. First of all, thermodynamic properties have been discussed, and among thermo means heat, dynamic motions, properties which change by changing temperature, they come under the topic thermodynamic properties. And in this slide I have chosen such a way, such a slide because in your 2020 edition group number are currently written group 14 for example, and in your textbook in this topic group 4A is written. In your old versions of book you find group 4A, but in new you can find both 4A as well as group 14. Group 14 consists of, it is also called carbon family, consists of carbon, silicon, germanium, tin and lead. Carbon is present, here is period, number of period, here are boiling points given, temperature is given, and there may be different boiling points of different substances. So we start with group 4A, which I have highlighted with blue color. Carbon is the first element present in second period. In third period silicon is present. In fourth period germanium is present. In fifth period tin is present. So when these elements combine with hydrogen, they form hydrides. Binary compounds of hydrogen are called hydrides. There are two types of elements should be there. One is hydrogen and one some other element. All these are hydrides of group 4A are non-polar. So they have only London dispersion forces. As I have previously told you that London dispersion forces increase as we move down the group from top to bottom. Sorry. It's due to increase in the number of electrons, number of shells. Polarizability increases, electron cloud increases, and London forces become stronger, and as a result boiling points become increased in value. So all hydrides of group 4A, which I have shown with green color in the graph, they have London dispersion forces and their boiling points increase as we move from top to bottom in a group. Next, further it can be explained that among the elements of sixth period, second period, and groups of fifth, sixth, and seventh, you find that in case of topmost elements, for example, in case of group 5a, here is ammonia. In case of this one is ammonia. In case of group 6a, here is hydride of water, oxygen, that is water. And in case of group 7a, that is HF. So these are top elements, and you find that they have highest boiling points among their groups. Reason is this: all these have hydrogen bonding. Due to hydrogen bonding, they have high boiling point. As we move to next period or down in the group, for example, in case of all these fifth, in case of all these groups, fifth, sixth, seventh, in case of fifth, after nitrogen you find phosphorus, so its hydride is here, that is phosphine. In case of I highlight rather than writing by pen. In case of HCl, after fluorine, in case of halogens, after fluorine there is chlorine, here is HCl. And in case of water, in case of group 6a, after oxygen is sulfur. So H2S, H2O, these are compounds which are lacking hydrogen bonding due to small electronegativity difference between hydrogen and sulfur, hydrogen and chlorine, and hydrogen and phosphorus. Definitely they either have dipole-dipole forces or London dispersion forces, which are weaker. As a result, they have low boiling points as compared to their respective top elements. Similarly, from now onward, London forces become prominent. When we go to third to fourth period, you find that are descending, are moving from top to bottom. For example, after oxygen is sulfur and after sulfur is selenium, you find some boiling point higher. Reason is that now size of selenium is bigger than that of sulfur, and London forces become stronger here. Same is the case with almost all the elements. In case of elements which are under discussion, in case of HCl or HBr, there is slight difference in their boiling point. Reason is that HCl has dipole-dipole forces, whereas HBr has weaker dipole-dipole forces and stronger London forces. In case of HCl, weaker London forces are there. So HCl has stronger dipole-dipole forces, weaker London forces, whereas HBr has weaker dipole-dipole forces, stronger London forces. So as a result of which, there is slight difference in their boiling point. Okay, next is something else. If you discuss only electronegativity difference on one bond and thereupon strength of hydrogen bonding, then of course HF should have stronger hydrogen bonding than OH. But in case of water molecule, you have two hydrogen atoms which are available in each water molecule for hydrogen bond formation to oxygen of another atom which has two lone pairs, and due to these two lone pairs, two hydrogens can form hydrogen bonds, and due to those hydrogen bonds, more number of hydrogen bonds, water has higher boiling point as compared to the HF. So that's why water has higher boiling point than these things have been discussed in our next slide. We move on to next slide. All these things have been discussed here. Group 4A is lower boiling points. Reason is I have explained everything. You are to read this through your textbook and also from this paragraph. You are to number 1, 2, 3, 4, all these things. We move on to our next. Solubility of hydrogen bonded molecules. You know that like dissolves like. If you have some polar molecule, it would have positive and negative end. So due to polarity, it can attract other molecules. And in case of water, there is possibility that anything that can form hydrogen bond with water molecules would be soluble in water. Similarly, hydrogen bonded molecules like methanol, ethanol, carboxylic acid. They form hydrogen bond among themselves. They can form hydrogen form bond with water molecule, and due to which they are soluble there. So like dissolved likes and polar substances are soluble in water. Cleansing action. Fats and oils are main part of stains that are at our clothes. Their molecules can, whereas soaps and detergents are alkyl or aryl benzene sulfonate. Detergents are aryl or alkyl benzene sulfonates, whereas soap is sodium salt of long chain fatty acids or carboxylic acid. So long chain fatty acid, carboxylic acid, they have polar and non-polar ends. Alkyl portion, hydrocarbon portion is non-polar one, whereas carboxylic acid portion is polar one. So non-polar is dissolved in, or non-polar becomes part of strains, and polar becomes part of water, due to which when we shake water, it moves away strains from our clothes. So cleansing action is also due to attraction between water and polar and soap molecule. Next is hydrogen bonding in paints and dyes. You know that wood is of cellulose, and cellulose is glucose, uh, which have OH groups. Paints and dyes have adhesive action to hydrogen bonding. Similarly, hydrogen bonding also makes glue and honey stick substance. Clothing. We use cotton, silk, or synthetic fibers for clothing. Hydrogen bonding is of great importance in thread making materials. This hydrogen bonding is responsible in the rigidity and tensile strength, how much it can be bent without breaking. That is tensile strength. So clothes, you know that either of protein like things, amides there, and or some carbohydrates there, so due to which hydrogen bonding can be possible there. Food materials, you know that carbohydrates are carbohydrates, you may know that polyhydroxyaldehydes are ketones. They have polar groups. Hydroxyl group are there, they can be available for hydrogen bonding. Glucose, fructose, sucrose, each of them contains OH group, which is responsible for hydrogen bonding in them. Hydrogen bonding in biological molecule. This is something more important for medical related students, although it is knowledge and equally important for every student, but in their field it is more applicable. So structure of proteins, you know that they are formed from amides, and their primary structure is sequence of amino acids. Secondary structure of protein may be alpha helical structure or beta pleated shape. These alpha helical structures of the secondary structures of proteins are beta plated structure. They are due to the hydrogen bonding. Similarly, you can find hydrogen bonding in hereditary materials. DNA is double helical structure. These strands, double stranded structure, and these strands are linked together through hydrogen bonds. So here I have tried to explain this. In case of DNA, you have DNA, you know that polymer is of nucleotides, and nucleotides have, among other things, nitrogenous bases, phosphatic groups, and other things are there, but main thing is that is for our interest, that is hydrogen bonding. These are complementary nitrogenous bases, guanine and cytosine. You are watching at top, it forms 3 hydrogen bonds here, you know, 1, 2 and 3. It forms 3 hydrogen bonds. At the same, cytosine is one strand and guanine is another strand. They are complement. They are in front of each other, as a result of which hydrogen bonding is developing here. And due to these hydrogen bonds, double-stranded DNA molecules exist. Similarly, thymine, you can find here, adenine, they can form. They are also you may call complementary nitrogenous bases, and here oxygen is with this hydrogen forming a covalent bond. Hydrogen of this nitrogen is forming this lone pair of this hydrogen bond. So due to these hydrogen bonds, cytosine and guanine 3 hydrogen bonds, and thymine and adenine 2 hydrogen bonds, double stranded DNA structure is possible. And how is that double stranded DNA structure look like, you may watch this on our next slide. This one is there, double stranded structure is, and these are hydrogen bonds here, which I have just explained. So we move on to our next slide. Here is the secondary protein structure, that is on the right hand side. You are watching alpha helical structure. This one is alpha helical structure. Within the same single strand, spiral like structures, and this spiral like structure, and this spiral like structure is due to hydrogen bonding. And at the same time you find here, that is left hand side, beta pleated shape. This one, in beta pleated shape, you have nitrogen here bonded covalently with hydrogen, and at the other hand carbonyl group oxygen. So this oxygen lone pair and this hydrogen forms hydrogen bond. Similarly, here is hydrogen bond, here is hydrogen bond, here is hydrogen bond. So due to these hydrogen bonds, beta pleated secondary structure of protein is possible. And on the other hand, due to hydrogen bond, alpha helical structure is possible. So further explained here is alpha helical structure of protein. You find here, red you consider oxygen, and white you consider hydrogen. So hydrogen bonded with blue nitrogen, and on the other hand with oxygen through hydrogen bond. So spiral like structure due to hydrogen bonding is explained in this diagram. Next we'll move on to properties of liquid. You just read the word adhesion. Adhesion is the intermolecular attraction between like molecules. Unlike molecules. Adhesion is the intermolecular attraction between the unlike molecules, and cohesion is the intermolecular attraction between the like molecules. Here it has been explained, and to small extent you may say. On Monday, Noam Chomsky addressed Pakistani students through Habib University in Karachi, and he stressed Pakistani students to focus on science. And of course, no future is of any country without character and without science. Both these things are as complementary as you have observed in case of DNA. Complementary nitrogenous bases are. Liquid crystal, last topic is in reduced labels. You know that before discussing in detail this topic, liquids are substances which can flow, in which particles move from one place to another. They are considered as liquids. And crystal are substances which have specific geometrical shape, in which particles are arranged three-dimensionally in a well-ordered manner. And you simply keep in mind this concept very easily. If something is with ordered arrangement and as well as its particles are moving, then that substance is, of course, nothing other than but liquid crystals. So we move on to this one, definition. First of all, in case of here is definition: the substance which can flow like a liquid and also have some of the properties of liquids with a certain temperature range are called liquid crystals. Second definition is intermediate phase lying between the solid phase and the normal liquid phase is called liquid crystals. Further slides will explain further it. Liquid crystal, here is a liquid phase, and you can see at the left hand side, that is this one is solid, pure crystalline solid is. At the right hand, extreme right side, you have pure liquid is. In is no degree of order in case of liquid. There is no degree of order among the particles in case of liquid. Now, which we have circled at right hand side with purple color, that is transparent liquid, and on the left hand, extreme left hand side, which I have encircled, that is solid, and which there is, you know, that there is almost 100% ordered arrangement of particles. In between these two extremes, I try to highlight it with some different color, and circled with this blue color. You see that particles have some sort of ordered arrangement there, but not of 100% like solid left, and not complete disorder as in case of liquid. So this intermediate phase is called liquid crystal. A fluid phase in which liquid crystal flows and will take the shape of its container. It differs from liquid that there are still some orientation order possessed by the molecule. I move on to next slide. Later on I shall come back to this slide again. Clostridyl benzoate showed two melting points each. The crystal of this material melted at 145.5 degrees centigrade into a cloudy fluid. Turbidity appeared, which upon further heating up to 178.5 degrees centigrade became clear. So the temperature range from 145.5 to 178.5. Within this temperature limits, a substance turbidity, a milkiness was observed, and from clostridyl benzoate, that state was termed as liquid crystal. So if I move to previous slide, and we suppose that we are dealing with clostridyl benzoate, then where should be these temperature ranges? 145.5 and 178.5. 145.5 and 178.5. So I place these values here. If this is 145.5, I write it with some different colors. Here is, this should be 145.5 and this should be 178.5. So that's in between these 145.5 to 178.5. This substance will be in liquid state. If we are considering this, which one? Clostridyl benzoate. So clostridyl benzoate solid, clostridyl benzoate solid here, this one. On the left hand side, solid clostridyl benzoate, liquid crystals, and from 145 to 178.5, and above 78.5 transparent liquid. This one, the history, I have already explained this. So you are to, liquid crystal state exists between two temperature, melting temperature 175 in this case of clostridyl benzoate, and clear temperature 145.5 to 178.5. Uses in daily life. Liquid crystals can be used as temperature sensors. These are just to keep in mind. Every sentence has complete demonstration which needs a lot of time, but I just going to give you hint there. This is because the liquid crystal change their color with change in temperature. They are used to monitor temperature changes where conventional methods are not feasible. Some of the modern room thermometers contain liquid crystal. They are used to find the point of potential failure in microelectronic circuits. They are used to locate the veins, arteries, and tumors when a layer of you know that uncontrolled multiplication is cancer of cells is cancer, and that is somewhat hard part of the body. So you paste liquid crystal there, and different color will appear, blue color usually appear there, and you can point out the spot where the cancer is. So it is this technique is helpful in diagnosis of different tumors. Liquid crystals are used to display number and letters of electrical devices, digital watches, calculator, and computer. Liquid crystals are also used in screens of oscillographs and TV. LCD, you know that liquid crystal displays there. That is very interesting physics topic is sciences, but beyond the scope of your syllabus or your level. So you are to keep in mind these things. Now the last topic is differentiate between liquid crystal from pure liquids or crystalline solids. I think the different things which we have discussed so far about liquid crystal have been summarized here again under this topic. A liquid crystal is a state of matter which is in between pure liquid, transparent, and crystalline solid. I will just explain with the help of beautiful diagram. Crystalline solids, liquid crystal, and pure liquids. You can watch previous slide, and at the extreme left side where solid was written, you can write crystalline solid, in between liquid crystals, and on extreme right side with pure liquid. The liquid crystal resembles the crystalline solid in certain aspects, optical properties for example. However, pure liquids remain as such. Crystalline solid may be isotropic substance which show same intensity of properties in all directions is called isotropic substance. Anisotropic substance in which value of intensity of physical properties is different in different directions, they are called anisotropic substances. Liquid crystals are always isotropic. Pure liquids remain as such. Liquid crystals intermediate in between pure liquid crystals. Again these things have been repeated. Thank you very much for watching. I think to some extent it was helpful. It has been primarily focused on syllabus of first year chemistry of Pakistani students, and that is in case of COVID reduced syllabus. I hope this will be helpful to you to some degree. Thank you so much. Pakistan Zindabad. Allah Hafiz.